Yeah. Maybe it's okay. Okay. No, it's blocking me. I'm not in this row, so I didn't steal your seat. Instead, no. Okay, let's get started. It's a pleasure to welcome Sheng Chia. He's a member of the IAS, postdoc there, and he has very diverse interests. He works on gravitational wave astrophysics, works on beyond standard model particle physics, and yeah, he will tell us today about black holes as multifaceted probes of the gravitational universe.
Thank you, Prashant, for the introduction. Thank you for the opportunity to speak here at the BHI. Today, I just want to talk about how black holes are remarkably useful and effective probes of physics and astrophysics beyond black holes themselves. And I'd just like to start by conveying that, there's a sense in which that the black hole space-time is remarkably simple. Within the framework of Einstein's theory of general relativity, the black hole space-time solution is given by the so-called curve metric solution. And in that solution, the space-time is essentially only determined by two free parameters, which is the mass and the spin or angular momentum of the black hole. Of course, there's, strictly speaking, there's also charge for a current Newman solution, but in the rest of the talk, I will neglect charge because charged black holes are not believed to be astrophysically relevant. Just to elaborate on the simplicity of the black hole solution, if you consider any other astrophysical body, any other star, the sun, let's say, or neutron stars or white dwarfs, in those cases, in addition to the mass and spin, you would have to specify other independent parameters such as temperature, chemical composition, the magnetic field strength, so on and so forth, right? So just to highlight how simple black hole solutions are in some sense. So if black holes in isolation is all you care about black holes, this is kind of it. All you need to know is just the curve solution. Of course, in practice, we never observe black holes in isolation, but instead we always observe them indirectly through the astrophysical environment. One classic example would be in the case, interesting figures and sharing quite properly. One classic example would be the case where you have a binary black hole, basically two black holes that's orbiting around each other. And in this process, they actually emit gravitational wave radiation. So emitting some kind of sinusoidal-like waveform in that process. And as they lose energy and angular momentum in that gravitational wave emission, the orbit would shrink, and ultimately they would reach this merger regime where the two black holes would form a bigger black hole. So one of the central questions in gravitational wave astronomy these days is to understand when two black holes, you can kind of imagine there's one here, when the two black holes are orbiting around each other, how would they respond or react to the gravitational perturbations that are induced by its binary companion? For example, do black holes change their shape when they're in this inspired regime? Because it is known that if they do, it will actually leave measurable imprints in waveforms that you can actually measure and detect in the data. And broadly speaking, these kinds of response to gravitational perturbations are referred to as tidal effects. So just to make sure that I've clearly conveyed what tidal effects are, I think there's perhaps no more familiar example than the Earth-Moon system to understand what tides are. Oops. I've knocked off the so in the case of the Earth-Moon system, the presence of moon exerts a gravitational force on Earth. And as a result, there is a tidal deformation, a change in the shape of Earth. Specifically, in this case, it would be the periodic raising and lowering of tides that we observe on Earth. On top of that, it turns out that the presence of this tidal bulge, along with the orbital motion of moon around the Earth, generates a frictional force on Earth that transfers energy and angular momentum between moon and Earth. And this process, this dissipative transfer of energy and angular momentum, results in a phenomenon that's known as tidal locking, in which case the spin of moon along its own axis synchronizes with the orbital frequency in which it revolves around Earth. And this is the reason why we always see the same side of the moon from Earth. And this is a phenomenon of a dissipative tidal effect.
I guess the spin is coming outwards.
If the spin is coming outwards, right? So assuming that it's,
Yeah.
that's right, that's right. So more precisely, there are two types of tidal effects. There are the so-called conservative effect, which characterize the deformation of the body, and the tidal deformability of the body are described by a set of parameters that's known as the love numbers of the body. On the other hand, there are the so-called tidal dissipation effect, which are characterized by the viscosity, the frictional property of the astrophysical body. And again, this tells you how efficient the transfer of energy and angular momentum between the body and its external environment is.
Do they lock?
Huh?
Do the two spiraling black holes lock?
It turns out that in the case of binary black holes, they're never efficient enough to lock. If in the progenitor, in the case where you have a black hole and a big star, let's say, before the star collapses through supernova and form a black hole, and in that process, there can be a locking. There is a regime in parameter space, the black hole has to be close enough to the star and all that in order for this tidal locking phenomenon to be efficient. And that is in fact a proposed mechanism for sort of observing highly spinning black holes in the gravitational waves, emission when they're close to merging. So again, one of the central problems in black hole physics and in gravitational wave astronomy is to understand, what are the love numbers and viscosity or dissipation numbers of curved black hole. So here is a segue. Oh, by the way, I just noticed that there's like this Venn diagram of 5 quadrants of the branches covered by the BHI. One of them is history of science. I suppose this is the linear history of science slide that I have prepared. So some of the audience may be curious why the tidal deformability parameters are known as love numbers. Turns out it's named after a geophysicist in the 19th and 20th century. A.H. Love, who at the time was precisely considering or trying to understand this question of how Earth will respond to the perturbation that's sourced by moon. So here is the linear relationship of this tidal deformation. Delta Q is the induced change in the quadrupolar structure of a body that gives rise to this quadrupolar deformation. E is the external tidal field, and the constant of proportionality of this response is what is known as the love numbers. Here's a table which I extracted from a classic astrophysics textbook, which shows what the love numbers are for various celestial bodies. In this case, all of them in the solar system, subject to a given perturber. And you see that the love numbers are all different. And the importance of understanding the love numbers of a body is that it gives you some information about the internal structure or the internal composition of the body.
It's a measure of this
How much?
Yeah,
Yes, it's a measure of given a unit of perturbation, how much would the body deform? So the larger love number, it's much easier to change its shape. And in the limit where k is small or even 0, they do not. A final slide on this on the history of science slide. As you can imagine, there is no shortage, given these are called love numbers, there's no shortage of playful choices of words in the titles in the love numbers literature. For example, there are the so-called I love Q relations, which are empirically observed scaling relationships between the love numbers of neutron stars with its second order moment of inertia and its spin-induced quadrupole moment. Obviously, I'm not going to go through all of them. Maybe except just to point out that this is one of my favorites because I'm one of the authors.
In the numbers that you showed before, is it normalized between 0 and 1 or something like that? Or?
So in this case, K2 is dimensionless. You will peel off like the mass dependencies. But other than that, it is unbounded. K2 in principle, typically we would say that K2 is order 1, but really it is subject to. Okay, for example, when it depends on your choice of radius. So I've omitted like dimensionful parameters such as the radius of a body, right? if you have a body with a continuous density, sometimes it's not clear how you define the radius, right? And so, you can say that the radius is defined as, the separation at which it contains 99% of the mass, for example. But in that case, the definition of this K2 can actually change. I will show you a definition of Luft numbers, which is actually invariant to those types of ambiguities later on. Okay, so again, there has been recent progress and advances in understanding what the Luft numbers and the dissipation numbers of curved black holes are. And in the first part of the talk, I will elaborate on these results and shed some insights to that. Specifically, I will show that it turns out that curved black holes have zero Luft number. So this is the limit where, again, in the strict static limit, which I'll come back to, elaborate what static means later on. In the strict static limit of a perturbation, curved black holes have vanishing Luft numbers. So in that limit, they really do not deform subject to such perturbations. Intuitively, it kind of makes sense because black holes are sort of the most compact, gravitationally self-bound body out there. So you can intuitively guess that they're resistant to change when they're perturbed.
But they do perturb eventually, right? They
do. That's right. So that's right. Ultimately, if you think of a binary black hole, they do ultimately merge into one, right? So in that sense, there's a change in the event horizon, so to speak. Here we're focusing on in the limit where it's a weak perturbation.
But
in the inspired regime.
so when they're dynamical, they're not zero.
They are not. That's right. And with the dynamical,
They're still.
I'll explain that. That's right. And this is where your work comes into play. Yes, that's right. And observationally, people really only care about, in fact, KE to the 2. So the leading order Luft number, because that's the only Luft number that we can measure in the data, and the rest is really sort of too far-fetched from an observational point of view. On the other hand, tidal dissipation for rotating black holes has actually been understood for quite some time. The idea is that, intuitively, you'd imagine what the event horizon of a black hole would do is that it's this one-way membrane, where if you have an infalling observer, or you lose energy and angular momentum into black hole permanently. But it's interesting that there's a limit where if the spin of the black hole is high, you can actually extract energy and angular momentum from a highly spinning black hole. And this is the phenomenon that's known as superradiance. And I'll come back to this phenomenon later. So, why is understanding what the black hole Luft numbers and dissipation numbers useful? In the case of Luft numbers, knowing that black holes have zero Luft numbers actually is a very important baseline in gravitational wave astronomy. For example, in addition to binary black holes, we also observe binary neutron stars, and neutron stars, or in fact, any other stars, K2 is non-vanishing, right? So the Luft numbers are actually non-zero. What's more, there's this better parameterization. There was a question on this, which is ultimately what we measure, not this individual dimensionless number. So lambda is what we ultimately measure. And it turns out that this lambda that we measure depends very sensitively to the radius of the body divided by the mass. So this ratio, R over M, is sometimes known as the compactness of the body. So it depends, to the 5th power of this. So, measuring the Luft numbers of a two-body system in waveforms would actually be informative of the nature of the binary components. And in fact, in GW17, which is the first binary neutron star that we have detected, from there, and by measuring the Luft number imprints, the LIGO-Virgo collaboration has been able to place a bound on the Luft numbers of the individual neutron stars to the order of, let's say, a few thousand, a few hundreds or so in the appropriate units. And in turn, this allowed them to place a bound on the mass radius relation of neutron stars.
So what's the K that's implied by that? So lambda 2.
So lambda is what we ultimately measure.
Right.
K is just some order parameter that depends on the microphysics, so the nuclear equilibrium state of neutron star. And then there's also the macroscopic.
Can you deduce a K2 from the measure of lambda?
Just from gravitational wave alone, probably not. You would need sort of, let's say, NICA or other X-ray from other observations.
You have some idea of its mass and its radius.
People have some. So given if you specify a given nuclear equilibrium state, people have been able to compute sort of theoretically what K2 is. But there are like hundreds of different models of neutron stars, and so each of the models have different values. There's a rough range of, let's say, older one is also like the typical value that we
But experimentally, R and M are not measured. Maybe it's using some other way, so that
R and M. Let's see.
maybe it's using not gravitational waves, but other ways.
So in gravitational waves, you can actually just measure the mass of the component. And then from lambda, you measure R of M. So that is sort of an indirect measurement of R separately. Does that make sense? Yeah, so imagine these are just black holes. Even just from binary black holes where there's zero left numbers, you can measure the mass already. Right. And now if you have binary neutron stars with left numbers are non-vanishing, you actually measure basically R. The radius.
But there's a degeneracy between K
There's a
and R.
degeneracy. Yes, there's a degeneracy. That's right. That's right. That's right.
But you can also get R from like nicer.
Yes, that's right. That's right. You can get R from nicer. So that is, people have discussed maybe that's a different population of neutron stars.
from what? What?
Oh, nicer, which is a
There's
It's an X-ray satellite.
an X satellite.
Observatory. But you can measure R perhaps, but on other systems, not this guy.
Yes.
Right.
This guy all we saw was
You would say
gravity.
that's probably in the same class.
Yeah,
And
right.
then you get an estimate of.
Then you get the estimate of K or
Yeah.
effectively equation of state.
Right.
Yeah, which models are acceptable and which are not.
But it's really a mess because the neutron stars has different equations of state for the different parts of it, right? For the deep.
That is like another layer of complication. Right now, the assumption has been that, this is why black holes are so simple, mass and spin curve solution, that's it. But neutron stars, some have argued that, like maybe different population of neutron stars have different nucleation states, right? And they obviously have different radius, right? They have different histories of formation. So, right. The black holes are cool. K2 is 0, so no matter how big the body is, it has 0.
And so I guess, sorry, so the range of possible neutron star radii is very small, but it's a to the fifth dependence, right?
Yes,
So
that's
you
right.
get a little wiggle room.
That's right,
I
that's
see.
right, that's right, that's right,
I see.
that's right.
Right.
Right. So being a bit more speculative here, there are a flurry of proposals of what other types of exotic convex could be out there in the universe. I'm not going to go through in any detail, except just to say that in virtually all of these cases, the K2 is non-vanishing and the radius can be very big. It depends on the microphysical properties of the additional particle, let's say. But typically R can be very big as well. And so left numbers that we measure can be very big. And in these cases, the imprints, if they're in a binary system, say you have an exotic body and a black hole, the imprints on waveforms could be measured if lambda is big. And this is why understanding black hole zero left number is sort of important baseline. So that was for left numbers. In the case for black hole dissipation, there's in fact a very well-known phenomenon, probably 50 years by now, where this emergence of a highly energetic jet from the center of galaxy, in this case the MEV7, sort of directly generated by having an accretion flow and strong magnetic fields around the supermassive black hole at the center of the galaxy. Of course, I'm speaking at Harvard. This is the classic direct imaging of the MEV7 black hole. I saw this a poster of all of the newspaper headlines of this image. And just to say that black hole dissipation and superradiance is actually very well understood in the astrophysics context. And just to elaborate on this process of launching highly energetic jets is often known as Gravitational process. It's also remarkable that the same superradiance process is a very powerful probe of dark matter physics. So there are many different proposals of what dark matter could be, but if all or subcomponent of dark matter consists of ultralight bosons or wave dark matter, sometimes also known as fuzzy dark matter in the literature, then through superradiance they can actually be spontaneously form a bound state that surrounds a highly spinning black hole. And the way it works here is that if the Compton wavelength of the boson field is comparable to the size of a rotating black hole, this field can extract energy and angular momentum from the black hole, such that the black hole spins down and outclowns a bosonic condensate that it's formed around this black hole. I think it's remarkable that it turns out the structure of this system is very similar to the proton-electron structure of the hydrogen atom. And these systems are therefore often known as the gravitational atom. The intuition behind this is that in the case of the hydrogen atom, you have a proton at the center and a cloud of electron wave functions surrounding it. And they're bounded to each other through a 1/r electrostatic Coulomb potential. In the case of the gravitational atom, instead you have a black hole at the center, and you have a cloud of boson condensate around the black hole. And they're bound to each other through a 1/r Newtonian gravitational attractive force. And in fact, this analogy is not just qualitative, there's a precise mathematical relationship between the two. And in the second part of this talk, I'm gonna elaborate on this a little bit. Just to make sure that you don't think this is some crazy idea, this that all the ingredients that's needed is just pure GR and a ultralight bosonic field that is minimally coupled, so there's no axion, no like self-interactions involved in the matter sector. All you need to be lucky in some sense is that the Compton wavelength of the field or its mass sort of is comparable to the size of a highly spinning black hole. So here is a numerical relativity simulation that shows how these clouds are formed, which has been conducted years ago. All it shows is that
any wave hitting the black hole gets a boost through the superradiance effect. And then what happens? Then the resulting.
I will show exactly a slide. So
Okay.
in the limit where the frequency of the field is lower than the mass, you can form an instability. So you can form ultimately a bound state around this black hole.
Okay.
That's right.
The black hole
fact,
has to be rotating though,
Yes, the black hole has to be rotating.
so it's not for Schwarzschild, there's no, so
Yes,
they
Right.
need to be,
In order to have superradiance.
right.
yes.
I understand that. I was just trying to understand, like, what is it about the superradiance that puts it into orbit? These are two separate things. One is it gets a boost, and then the second is.
It gets a boost. You're jumping ahead. In fact, I have a slide precisely on that. But it gets a boost, but ultimately you can think of having the mass of the boson field acting as a
I'm not trying to
mirror.
derail your orderly sequence of thoughts.
That is fine, Just to say that it will get reflected, and this process, superradiance amplification, can keep going on and on until you form an unstable process and form the cloud. Okay, so I understand that I was told that the foundations seminar is targeted towards a broad audience with a diverse interest and background. So I hope the intro was clear. In the rest of my talk, I'll be a bit more technical, I'll be a bit more precise with equations and all that. And this is probably, so for the physicists and astrophysicists in the audience. Any questions before I move on to these two topics? Okay, if not, we already had my number. So in order to understand tidal response in GR, I think it's important, is instructive for us to take a step back and understand how tidal effects are formulated in Newtonian gravity. In Newtonian gravity, a body would respond to the perturbation that's being sourced by a binary companion. In the case of a static limit, it would respond by acquiring induced mass moments. So delta Q is the induced multipolar structure in all orders in multiple expansion of the external tidal field. E is the external tidal field, again, in all orders in L and M, the multiple expansion of the tidal field. You can infer from dimension analysis that this relation has to scale with some power with radius. And then the overall constant of proportionality is what we call love numbers. Previously, I showed K2 because that's strictly only for the quadrupolar, the L equals to 2 love number, but really strictly speaking, there's a whole hierarchy, there's a whole set of love numbers for each moment.
Actually, in this, when you say static, you mean the perturbation also is very small?
That's right. So in the limit where you consider this is just static, where imagine this is not moving. Okay, in that limit, there's no time dependence in this response relation, and this is all you have. But of course, in practice, the perturbator is not static, but it says moving around the body, and so the response is dynamical. Okay, by dynamical, I mean that now there's a time dependence where the induced moment is given by the convolution of the external tidal field multiplied by this function f here, which is the total response of the body. But the nice thing is that, so this is in general complicated if the orbit is fast moving, but in the limit where the external tidal field is slowly varying with time, one can perform systematic expansion in time derivatives, and you obtain the second line here. Where leading order, you restore the static tidal term that I showed earlier on, but now there's a new correction to to the tidal term, which is proportional to E dot, the time derivative acting on the external tidal field. And this is tidal dissipation. It has many names to it: tidal heating, tidal acceleration, so on and so forth.
So on the previous slide when you showed it, it doesn't matter what the static configuration is. It does not need to be spherically symmetric or something.
Yes, it doesn't matter what the static configuration is. All of the details of the nature of the perturbation is encapsulated in so overall order one coefficients associated to the tidal moment. That's right. So this is dissipation, and the easiest way to understand that this is a dissipative operator is the fact that this term involves a single power and time derivative. So it is not invariant at the time reversal, and therefore it does not conserve energy. Nu is the dissipation numbers of viscosity of the body, and tau naught is the typical delay times here. Associated to this effect, it is well known indeed that this viscosity-induced time lag introduces a phase difference between the direction of the bulge and the direction to the binary companion. So this is the relation in the time domain. And obviously, convolution in the time domain is just product in the frequency domain. And if one performs a Fourier transformation, you obtain this relationship, where now omega is the frequency of the external tidal field. But now this total function f takes a very simple form, given as follows. The key takeaway from this slide really is that in order to distinguish the conservative piece from the dissipative piece in the response function, you read off the real and imaginary parts of the total response function. So this sounds obvious, but it turns out this simple but crucial observation will play an important role in teaching us how would we read off the response function of black holes in GR.
Could you go back to the phase? I didn't fully understand what is the phase. There's a phase, the viscosity is caused.
Right. So there's a dissipation. So with a dissipative term, there's a typical delay timescale associated to this process, and that delay introduces a phase difference. The fact that the perturber will come, there's a time lag in the response of the body subject to the presence of this perturbation. Does that make sense? We observe it in the Earth moon. Okay. So real is for Luft numbers and imaginary terms are for dissipation. And hold that thought. So how do you read off the response function in practice? In Newtonian gravity, you read it off through the potential, where leading order one just has the classic Newtonian 1/r potential, which assumes that these are point particles. But of course, in the presence of a perturber, you have additional corrections coming from the external tidal field E. And in this term, there are actually two broad classes of terms. There are the so-called growing term, because it scales as positive power of r. I should mention r, little r is the separation of the body to the perturber. So these r to the L factor are so-called growing terms, and these are contributions, the direct contributions of the perturbation to the potential. But they are also the so-called decaying terms, excuse me, the decaying terms, which arises due to the response of the body to the perturbation. And the overall coefficient that appears before it are the response, the total response of the body. So this is in Newtonian gravity. In GR, we do not work with the potential, but instead we work either with the metric or something that's known as the Wild scalars. I won't go into the details. Some in the audience may know what the Wild scalars are, but just to say that these are scalar quantities that involve projections of Einstein's solutions, vacuum Einstein metric solutions into a set of null tetrads. Again, I won't go into details, just to say that these are a set of nice quantities that we can work with in GR. And the reason for that is because of the Tucholsky equation. The Tucholsky equation is a set of ordinary coupled differential equation that solves for the linear perturbations around a curved black hole background space-time. So the upshot, again, I'm skimming through a lot of the technical details. The upshot is that one can solve the Tucholsky equation and read off the total response function for a black hole. In the case for Schwarzschild black hole, I'll talk about current black holes for a bit later. But in the case for Schwarzschild black hole where there's zero spin, the total response function has the following form. We see that the leading order real term is zero. It's funny because when you solve these things, Mathematica spits out just I omega, and you have to infer, where are the left numbers? But it's zero, so it doesn't show you that zero. So it's funny when I first encountered this, I was a bit puzzled, but it's zero. I mean, the left numbers of Schwarzschild black holes are zero. And indeed, this fact that Schwarzschild has zero left numbers has been known for some time, say in 2009 or so. So with this approach, we're just recovering some results that's been understood in the literature for a while. The nice thing about solving things in the Tucholsky equation is that one can derive the dissipation numbers for Schwarzschild black holes for all orders in the multiple expansion of the external tidal view. That's something that was missing in the literature.
So, question here. So I've got a Schwarzschild black hole. I've got this perturber out here, right? And this analysis says the love numbers are zero, which, going back to the earlier discussion, means that I'm not able to distort the horizon. It's a sphere, still a sphere. Okay. Now, fine. But is there a way of looking at the horizon in this perturbed space-time and showing that locally it's whatever intrinsic curvature or whatever is constant over the whole sphere?
Yeah, there's a sense in which there's an infinite choices in which one can choose an observer close to it, which shows the D-forms. Because in GR, things are so gauge dependent.
That's what
there are a set of apparent horizons, right? Infinite choice of apparent horizons that we can choose. The way these left numbers are, so the physical quantity of these left numbers ultimately is determined by what this imprints, how these coefficients are left in waveforms. That's one answer, one partial answer. So waveforms are observables, they're not gauge ambiguous. The second thing is that these are actually, so you can think of them as actually a set of induced multiple moments that are measured at asymptotic infinity.
Yeah, that part I understand. Yeah, we are doing everything asymptotically. But there is also a well-defined, the whole thing is static, right?
Yeah.
There's a well-defined horizon.
Yes.
So is there something that the geometry of the horizon can tell you it has not been distorted?
The geometry of the horizon.
Yeah, if this is a well-known concept, I don't know.
Yes, I have to think about that, but it's very interesting. It's a very interesting question.
Because certainly in the Newtonian examples, I can go on the surface of the neutron star and say, this guy is a little longer this way and less on that side. It's a measurement I can make.
Yes.
I was just wondering if there is the equivalent for the black hole.
I'm not sure if this question is well defined. The horizon is
yes.
This is why I'm putting all these,
Right.
This is why the partial answer there would be the whole notion of apparent horizons in GR, which complicates a lot of the formulation of that question.
Right.
It's always tricky, right? All these gauge ambiguity.
But because it's static, it doesn't have to be an apparent horizon.
That's true.
There is a true horizon there, which we can calculate.
That's true.
So the question is,
It's true. I'll think about it. I'll get back to you. We can chat after this seminar. This is a slide where I just want to juxtapose and clearly compare the response of the Newtonian body and the Schwarzschild black hole, where you can see that the left numbers of black holes are zero. And now, if you look at tau naught and compare it to what we have here, it kind of makes sense because for a Schwarzschild black hole, the only relevant time scale is m, the light crossing time of the black hole. And indeed, the typical delay time scale, so Schwarzschild black hole is 2m as well. One interesting fact about that's unique to Schwarzschild black holes is that in the strict static limit, when omega is zero, not only are these the leading order dissipation terms vanish, but all high order corrections, the omega squared, omega cubed, they all vanish as well. And the left numbers here is zero. And so it's interesting that somehow for a Schwarzschild black hole in the strict static limit, it does not respond at all. This is, of course, very different in the case of a rotating black hole, where there we have a new time scale, which is the spin of the black hole. Where there, even in strict static limit, one would still, the curved black hole can still respond. So the upshot is that one can repeat the same exercise, solving the total response of a curved black hole using the Tucholsky equation, and this is the result, where you see that leading order, the real part of the total response is zero. So the left numbers of curved black holes are zero. It's very important to emphasize that this vanishing of left numbers is true for all values of black hole spin. It's true for, I didn't explain this earlier, but it's true for both the electric and magnetic perturbations in GR, the electromagnetic tidal moments, and it's true to all orders in the multiple expansion of the external tidal field, assuming that in the limit where these are still linear perturbations. Okay, and this generalizes some partial result that's been derived in the literature beforehand. On the other hand, in terms of the imaginary term, this is the curved black hole dissipation. The key point here is that there's this pre-factor here that's known as the superradiance factor, where in the case where the spin of the black hole is 0, the sign of this term is negative, and this is the case where one would sort of lose energy and angular momentum to a Schwarzschild black hole. So probably agrees with what your intuition of what a black hole does. But the opposite case where the magnetic azimuthal mode is positive and the spin of the black hole is high enough, you can have the case where the sign of this term is flipped. And so one has the opposite phenomenon where one can spontaneously extract energy and angular momentum from a spinning black hole. And this is sort of one of the proposed mechanisms. In fact, my understanding from people who work in the EHT collaboration is that this is a main sort of mechanism for launching the M87 jet that we discussed earlier on. So I won't go into the details except just to say that there has been work which try to constrain the Love numbers and dissipation numbers of black holes in gravitational wave using the set of all the 100 binary black holes that we've detected so far. Again, won't go into the details, but for individual events, one can see that the constraints on the Love numbers and the dissipation numbers are not particularly strong, but one can actually improve on the results by stacking the results of individual events to obtain a population constraints, and that is actually work in progress. They're hoping to put it up soon. Okay, so that was for black hole tidal events. Do you have any other questions? Yeah.
Not black hole, but let's say you have a boson star.
Yeah.
But in GR.
Yeah.
Would you get non-zero Love numbers?
Yeah.
Immediately?
Yeah.
And also, like, is there a sense of what the time, like the delay time would be there? Would it be some something related to the mass of the boson star, like at the mass term reaction?
So these are two separate questions.
Right.
The Love numbers is actually, so it turns out, when I calculated this vanishing result, it turns out a key ingredient in the vanishing of black hole Love number is two things. One is that you impose a boundary condition at R plus, at 2m, that's like for Schwarzschild. The other thing is that it's important that you're imposing this only ingoing wave condition at the event horizon. Right. If you change either of those, if you allow for the boundary condition to be slight leakage, slight outgoing wave energy, the black hole Love number would be non-vanishing. Okay, so it's very. I mean, you can probably cook up, come with some contrived boson star example where this is still true, but I think it's hard to mimic that two conditions for a general body, which is neither as compact at R plus and not like purely event horizon.
So if I were to do this not at a horizon, not at an event horizon or a killing horizon or something, I just impose ingoing boundary conditions.
Yeah.
Would I still get
if it's ingoing boundary condition, but at R larger than R plus, no, it would still be non-vanishing. Okay, but the other question on dissipation on the typical delay times is completely separate because these are two orthogonal sectors, right? And then again, you would have to compute the absorption cross section, for example, of the boson star that you have in mind. Yeah, so two separate. Of course, the nice about black holes is that with Minkowski equation, once you solve it, two drops out. But for a general object, for neutron star, let's say they're different. So for example, in the case of neutron star, to obtain the Love numbers, people have always just focused on the diagonal terms of T mu on the momentum tensor. So just look at the pressure density relation. In order to understand dissipation, you need the off-diagonal terms, the anisotropic pressure terms, because those are the terms that tell you what how viscous the body is. So it's almost like you specify different microphysics to get those two sector responses.
So would this be like TT5 or is it like TT5 or the space as anisotropic?
Yeah, TT5. That's right. That's right. The mixture between the time and spatial directions.
So this slide was a little bit too fast for
this one.
Yeah.
Sorry. So yeah. So I can explain a little bit. So lambda tilde is actually a mass weighted Love number. This is actually the most precise Love number that we measure. So you have lambda 1, lambda 2, but it turns out what we measure best is a mass linear combination of lambda 1 and lambda 2, and that's in the gravity wave literature. That's what we always call lambda tilde. you see that it kind of peaks at 0, but the likelihood is only tells us the SNR of each of these events only high enough to say that we're ruling out lambda tilde at like a few thousand or so. It doesn't here in this small lambda tilde regime, we're still prior dominator. So we don't constrain, the data doesn't tell us much here. But future detectors will be able to do that. We'll be able to constrain this the precision to be a very small value. And the same is true for dissipation numbers.
That's dissipation.
That's for dissipation numbers, yeah. Yeah, sorry, I should explain this a bit better.
So the bottom line is that right now it's not sensitive enough.
That's right. The bottom line is we're not sensitive. The data is only tells us that extremely large values of dissipation numbers and extremely large values of Luft numbers are ruled out by the data. But it doesn't. But for the black hole theoretical value here would be like order 1, let's say, and this is 0. So.
And do you know if it's like expected to improve drastically?
We are doing a future forecast. We're doing a work which involves doing future forecasting with future, Einstein telescope, LISA, and all these futures third generation detectors to see how well we can do.
I see.
Oh, 15 minutes. So I will probably speed up a little bit. So this is the coming back to this simulation. The rest of my talk, I just want to explain the formation mechanism of the boson clouds. Oops. Okay, so this is the slide. This is the slide that Peter was anyway that we discussed a bit earlier. In order to understand the formation of this cloud, it's useful to think of a scattering process where if you scatter a wave, ingoing wave with frequency omega and azimuthal angular momentum number m into a highly spinning black hole with angular frequency that I call capital omega h here. Oh, by the way, this ratio of omega over m is sometimes known as the angular phase velocity of the medium. And in this process, the outgoing wave will have a slightly larger amplitude compared to what's being sent into it at the expense of extracting some little engine angular momentum from a rotating black hole. And by the way, this spontaneous emission of wave is actually analogous to something that perhaps some of the audience are familiar with, which is the Cherenkov radiation. In the case of Cherenkov radiation, you have a medium of hot water, let's say, and in that case, you have ingoing neutrinos, for example. And if the velocity of neutrinos is larger than the phase velocity of hot water, one can have spontaneous emission of light. And this is nothing, superradiance is nothing but the rotational analog of that process. Now, this is exactly the slide I wanted to show, where now with this one-off event, things would just go on forever. But imagine hypothetically, just as a thought experiment, that we place a reflecting mirror around the rotating black hole. And what that happens is that this wave gets reflected by the mirror, goes back to the black hole, extracts a little bit more energy, and out comes a wave that's slightly more amplified. And this process will go going on and on and on and on until the spin of the black hole reduces sufficiently for the inequality to be saturated. So this thought experiment is called the black hole bomb scenario. This proposed quite some time ago. Of course, reflecting mirrors, we have reflecting mirrors in realistic astrophysical environments, so this is a very contrived setup. But the nice thing is that having a massive boson field, a boson field with mass, naturally plays the role of a reflecting mirror. So if you plot the effective potential of the black hole, where in this direction moving towards the event horizon and in this direction heading towards large distances, you would see that in the presence of a boson, massive boson with mass mu, the potential is raised. There's a DC offset in the effective potential that levels up at a height that's precisely given by the mass of the boson field. And therefore, if you have a wave whose frequency is smaller than mu, once you have superradiance amplification, you backscatter, there's a potential well. And then this process will keep going on until there's an instability therefore. And ultimately, you will have a condensate, a bound state that's being formed in this local potential well. And that's sort of the intuitive reason why such a condensate can happen. So I'll show a little bit more equations because the superradiance phenomenon and the fact that you can form a boson cloud works for scalar field, massive vector field, and the results are very analogous. So I'm just going to show both of them. Where here is a Klein-Gaussian equation and here is a Brock equation. it's important to emphasize that the formation of these things only rely on the minimal coupled boson field, whose interaction is only between the mass of the boson and the metric of a curve black hole.
So I understand the picture you're giving, but is all the outgoing power confined, or is some little bit still escaping to infinity?
So in this limit, I think all of them are confined because in this limit, with omega small to mu, the leakage is exponentially down.
It is exponentially.
It is exponentially down. So you can look at the radial solution and see that in this regime, it's exponential. This is why it's a tail. This solution, this boson condensate is this tail solution with exponential tail.
So this means the condensate is just getting more and more massive with time?
Until the spin of the black hole is sufficiently small.
That's the only way it controls, not by leaking to infinity.
No.
Okay.
So
I mean, that's the supposition that it can't leak. Is that right? Or is that a deduction?
Deduction from these solutions. I mean, I don't understand it fully. Yeah.
Deduction from the solutions. So here, to explain the physics in more detail, it's useful to take the colorimetric and expand it large distances, where things simplify. Where now there are these m of r term, which is the gravitational potential, the fact that there's a black hole at the center, and these off-diagonal terms, which depend on the spin of the black hole. I'll come back to this, why this is important. In order to understand the analogy between the gravitational atoms and the hydrogen atoms, it is useful to define what we call the non-relativistic fields, this little psi and psi i's. And in this definition, what we're saying is that we're peeling off fast oscillatory behavior in these fields, such that these little psi's, they vary at a time scale that's slow compared to 1 over mu, which is the typical oscillatory time scale of the mass of boson. So if one plugs in this ansatz into the Klein-Gauss and the Proctor equations, we obtain Schrödinger-like equations for both the scalar and the massive vector field. And the fact that these are exactly sort of the the equations that govern the dynamics of hydrogen atom is sort of the reason why we call these things the gravitational atom. Like here, you see that these are like the kinetic terms in the Hamiltonian of a hydrogen atom. There are these one of our Coulomb-like potentials, where alpha right now is given by is often called the gravitational fine structure constant, and these are given by the ratio of the mass of the Schwarzschild radius of the black hole divided by the Compton wavelength of the boson field.
But is there must be some approximation here, right? Because
There is a so in this approximation, we're actually assuming that alpha is small. And I'll explain. So it turns out in order for the cloud to grow, alpha has to be smaller than order unity. And so having a small alpha expansion in deriving this equations is a valid thing to do. I'll show later what happens when you have high order than alpha.
yeah, because your alpha non-linearity is right.
That's right. There are non-linearities that scale as alpha over r. So alpha over r squared, alpha over r cubed, and all that. Those happen. So in fact, next few slides, I'll show that. So with this alpha, if you plug in typical values, you would see that, and as I briefly alluded to, in order for these clouds to form, alpha has to be smaller than order unity also. And so for a stellar mass black hole, you'd be probing bosons of the scale of 10 to minus 12 eV or so, which I think is very nice because, for those who are familiar with the dark matter literature, there are proposed mechanisms of how we can probe fuzzy dark matter using cosmological surveys. Those cases probe scales of fuzzy dark matter of the order of 10 to minus 20, 10 to minus 22 eV, so very, very long wavelength views. Here we're sort of in the intermediate regime, which is hard to detect using cosmology, but with black holes, we can do that. Okay. Given that they obey the same equations, it wouldn't surprise you that they obey similar solutions, where now, just like the hydrogen atom, if we expand the results in spherical harmonics, in scalar and vector harmonics, you would obtain radial solutions that are like Bohr, like radial solutions of the hydrogen atom. In addition, these solutions are governed by a set of quantum numbers, N, L, J, and M, where N is the principal number that tells you the overtone structure, or rather, how far is the peak of the radial field from the center of the gravitational atom. L is the order angular momentum number, J the total angular momentum number, and M is the azimuthal number. But for scalar field, J and L is the same because there's no intrinsic spin. But for a vector field, there are three independent polarizations which relate J and L in this following manner. Yeah, I might have to speed up a little bit. This is to your point where I just showed the equation at the leading order level, but it turns out we can compute higher order alpha corrections to the solution. And if you look at the energy spectrum for a scalar field, let's say, you obtain all these nice structure, which I'll explain now, where at leading order, with one of our potential, you have this term in the spectrum alpha squared over n squared, and these are like the Bohr energy levels of the hydrogen atom that is shown in the vertical axis here. At order alpha squared higher, the L dependence that starts to appear, and these are like the fine structure splittings of the hydrogen atom. And so these are shown on the horizontal axis. And if you go to one order in alpha higher, the azimuthal number starts to play a role. And this term turns out is proportional to the spin of the black hole. And these are like the hyperfine splittings of the hydrogen atom. And so what this is telling us is that the spin of the black hole acts like a magnetic field on the boson, because for now it splits the degeneracy of different states of M. So for a given N and L, I have 2L plus 1 number of states in my spectrum.
Yeah, but what is not completely clear to me is for any system, not just about the. If you look at distances large enough, you will see 1 over R potential, and you will get this solution.
At absolute large distance is 1 over R. You have to go closer and closer to see that 1 over R squared, 1 over R cubed, and so on. Yes.
But you will see it anyway, even without this mechanism, right?
You say that anyway, even without this mechanism.
Because just by expanding it large R, you would see.
Oh yes, but in order to form these things, which is what I'm going to talk next. In order to form these things, how do you form
the bound state?
Yes, how do you form the bound state to begin? And this is exactly this slide.
But you will have something maybe that is not a bound, maybe a scattering state, but that you can still solve in terms of.
Oh yes, you could, but maybe the solution would not be this, high density bound state.
Maybe it will be a scattering.
It will be a scattering, which just leads to infinity.
But just the fact that it's 1 over R squared.
Oh yes, that's right. Absolutely right. That's absolutely right. Yes. Here we're solving a 1 over R. So the difference between scattering versus a bound state is here. With a bound state, I'm assuming that the frequency is smaller than mu, and so it's trapped in the potential. With a scattering process, omega is larger, so one can lead to infinity. Okay. Yeah. So this is a key slide. I don't think I have more time because I only have a few more. But just to say that all I've shown is the similarities between the two types of atoms, but it's a key difference. The key difference being that in the case of a hydrogen atom, we impose a regular boundary condition at the position of the proton. And so all the states in the spectrum are stationary states. In the case of the gravitational atom, we have an event horizon of the black hole at the center. And by imposing this only ingoing wave condition at the black hole event horizon, we have only quasi-stationary states. So the frequency now has an imaginary term, which again contains this superradiance factor that I described earlier. And right now, you would see that for positive values of M and for highly spinning black holes, this term is positive, so one can spontaneously form these clouds through an instability because of positive growth in the imaginary terms. And so for a given value of N and L, I have 2L plus 1 number of states. And this is the M equals to 1 mode, and this is the growing mode, whereas the rest are always decaying states. There is in principle an infinite tower of growing states in the spectrum, but you can think of this state as being the ground state of the infinite hierarchy of growing states. And so in the scalar case, the dominant state is the N equals to 2 and L equals to 1 mode. So these are like the 2p configurations of the hydrogen atom. In the vector case, it's similar, except that now there are 3 independent polarizations. There are many more states in the spectrum. But the key difference now is that this ground state, this dominant growing state among this infinite hierarchy is the N equals to 1 and L equals to 0 state. So these are like the 1s state of the hydrogen atom. So it's more spherical in its shape. Okay, I won't go through details, just to say that computed spectra both analytically and numerically, and that they agree with each other. In the final 2 minutes or so, just want to connect, the story of the gravitational atom with the Love number story that I showed earlier, which is that, the fact that now you have a a dilute, somewhat dilute bosonic condensate around the black hole means that it has non-vanishing Left numbers, and one can compute. In fact, it has been computed that Left numbers are very large. It really depends on this alpha parameter, and it depends very sensitively to it. It can really be orders of magnitude larger than Left numbers of black holes and neutron stars. And if the system, this atom is part of binary, the induced phase shift on waveforms can be so high that that current methods that search for signals in the data that only use binary black hole waveforms would not be able to detect these types of more exotic compact objects. Won't go into the details.
But that depends on how much of this boson condensate you have.
That's right. Good.
That's constantly growing, right, in this picture?
Good. So constantly growing. So in this kind of analysis, we just assume that it has saturated superradiance inequality. So it has already formed a quasi-stationary state. And numerical relativity, the one that I showed earlier.
How do you saturate?
Oh, you saturate it by here.
I thought you have to bring the spins together.
Yeah. So the initial conditions is to have a highly spinning black hole with the wave condition of this form, and then as superradiance proceeds, the spin of the black hole would decrease, whereas this is fixed. It would decrease sufficiently such that at the end you saturate this, and then the cloud would
Okay, so that is the same condition. Okay.
Yes, it's the same condition. And the numerical relative simulation that I showed here has found that depending on the initial spin of the black hole, in the most generous case, where this is a maximally spinning black hole, you would have about 10% of the mass contained in the cloud. If the spin of the black hole is 0.5, it would be half of that, roughly speaking. So it's still a sizable fraction of mass. If a 30 solar mass black hole is like 3 solar mass in the cloud, which is very non-negligible. And so therefore it can have very sizable imprints and gravitational waveform. Not going to, I wasn't planning on elaborating any of this, just to say that, in fact, in the Thursday meeting, I'll be talking a little bit more about detection strategies in gravitational wave data analysis, and I'll be elaborating a little bit more on the current techniques, the benefits, and also the deficiencies in detecting anything other than binary black holes with current methods that we have in gravitational wave data analysis. I'm not going to go to all of this. So, I hope I've convinced you that black holes are wonderful probes of physics and astrophysics in many different dimensions. So finally, thanks again for the opportunity to speak here.
I have a pretty quick question. So I think I missed something pretty critical. The potential at large R that is acting as this mirror is set up by the cloud. Is that right?
The thing that's acting as a mirror is the mass of the boson, not the 1 over R.
I see. But so if you have no cloud.
So 1 over R is here. 1 over R is this thing. In the limit where you have a photon, where there's no mass, it would just be this potential would decay as 1 over R large distances, and you will not form a bound state around. You will not form a light bound state around.
I understand. No, but my question is, if you have no cloud, right? You have just a black hole sitting around. How do you need some trapping?
You need some initial conditions.
Exactly.
Oh, that's nice. I mean, it's just like how the Higgs field. This is a nice thing. These things can happen spontaneously through vacuum fluctuations.
Oh, okay, great.
Just as how the Higgs field,
Right, because then there will always be some omega that's satisfied.
There's a few fluctuations in our vacuum.
Right.
Right. And this is how the proposal of probing dark matter is precisely this point that if dark matter is this component of a matter component of the universe, they will spontaneously grow around the black hole.
Great, thank you.
Yeah, that's a key point. Yeah.
So following up on that, through the same picture.
Yeah.
If I think of this as a scattering experiment, where my dark matter particle comes in from infinity, does something around the black hole, that guy is already above the asymptotic potential, right? So it will scatter and go back.
Yeah.
So it's critical that you need to create these particles locally. You can't just get them in from infinity.
They cannot be high energy enough. That's right. In another way, the omega, that's right, the frequency or the energy of this incoming wave cannot be so high that it just be a scattering process instead of forming a bound state. That's right.
Right.
But omega, is this, you can compute. So this is actually omega, the real part of omega, where, how should I say? I mean, that's right. It has to be of that initial condition, but that omega also depends on alpha, which is mu multiplied by the mass of the black hole. And here, because these are balanced, these are always negative. So one can actually, just from the vacuum of the black hole, as long as these fields exist, can just be spontaneously formed. Yeah, that's a key point. Yeah.
But why can't you scatter away with a low enough energy that will be trapped?
Yeah, you can. I just
So
don't know
you can
how,
also-
like in realistic astrophysical, I mean, I don't know how you said how these things. Yeah, maybe if you have like if these fields do exist, and maybe they are scattered through some supernova explosion, if it interacts with neutron, I don't know, whatever. Yeah, maybe that could happen. But here, this is like the vanilla case where it doesn't depend on these kinds of other phenomena. It can just be spontaneously interacted from back in.
And also, for general question, the log numbers, how do they imprint on the signal
Oh, in the phase.
of the phase? And is there a
Most
phase?
sensitively in the phase.
Um,
It affects the amplitude of the waveform a little
no,
bit.
let's say in the stages of the binary merger, where is the most impact or
Yeah.
imprint? Is it in the ring down phase or in other phase?
So when we talk about Luft numbers, the only well-defined regime is the in spiral phase before they merge.
Ah.
So the Luft numbers will leave its imprint in the phase shift. It will introduce phases. It also affect the amplitude, but in GW astronomy, we're mostly sensitive to phase coherence. And so it's the shift in the phases that matters most.
But I think also it's not completely understood if, for example, the log numbers and the quasi-normal modes, if they may be, so if they're related to each other,
Yes.
you can also read them off from the.
In the case of a neutron star, any Newtonian body, one can write causal relationships. So Kramers-Kroneck's relationship that relates the Luft numbers, which is the response of a body, to how it's being perturbed and rained down. In the case of black hole, we tried with Misha, but there's some technical subtleties that makes it hard to prove that such a relationship exists. But we want to do that, but it's hard. You can see.
So you said that a stellar mass black hole would be sensitive to 10 to the minus 12 EV
10 minus
particles,
10 minus 11 or so.
minus 11. And then by the time I go to a supermassive, it's a much lower mass.
It's 10 to minus 15, so much longer wavelength. So the
Right.
bigger the black hole, you're much more sensitive to longer wavelength modes.
And in terms of practical applications, that is less interesting.
No. It's just that right now with LIGO, we're probing solar mass black holes, whereas 10 to the 6 solar masses or so, these will be for LISA in the context of gravitational wave astronomy. Now, of course, people have considered whether these black holes can be formed around quasars, but I think there's so much uncertainty between how these clouds, if they really exist, how do they interact with messy astrophysics and equation disk? And that is a huge unknown. And a lot of the focus in this topic, at least, is on the pure gravitation case, so to speak, in gravitational astronomy, where things are cleaner.
We live in a photon ring space.
Of course.
So now I've got this, substantial, say 0.1 of the mass is sitting in this fuzzy distribution. I didn't get an idea of how far out it extends, but if it is going anywhere near the photon ring, it's going to affect the photon.
No, it's farther than the photon ring. So it's
further than the
it's further than photon ring. So these are, imagine in the case of the hydrogen atom, there's a characteristic Bohr radius, which scales as m over alpha squared, and then alpha is smaller than 1. This is like order hundreds of the Schwarzschild radius.
Oh.
The photon ring is like 6m or so, right? But we're talking about order hundreds or so. So it is very dilute, and this is why in quasars, let's say, I think no one is brave enough to sort of understand or compute how the interaction between a very messy accretion disks on these scalar condensates are, and so that has been sort of left aside in the literature.
But there must be a mass range where this thing is not at 100 M.
Yes, there is.
But it's near about the photon ring.
Yes.
That is something that our imaging can actually explore.
Indeed. I've spoken to people at the EHT collaboration, which actually has considered in like
there are EHT collaboration here.
Yes. Back at the IAS as well. Friends who work on the topic. Yes, indeed.
Okay,
And
I
yes.
think that looks like
Yeah, I mean, there's these ultralight field constraints you get from polarization in the photon ring. I don't know if that would help in this case, because I think it's probing a very different master regime. But I don't know, there's hope. I'm
Yes, yes.
Yeah, although, these, maybe we should actually. close
Yeah,
the
sorry
meeting
for
before
taking,
this.
uh,
Yeah.
going over time.
Are there any
We can
other
chat
questions?
after.
No other questions.
That was great, thank you.
Thank you, thank you.
Very cool stuff.
Thanks.